Okay, so where we left off was we've introduced now the spin operators, the x, y, and z components of the spin operator, which I said are these 2 by 2 matrices for fundamental fermions like the electron or the neutrino, the quark, anything that carries spin. um, and so what I want to do is I want to test this. I want to test this commutation relation. So let's just take a look at our choice here of spin operators, and let's apply it to this commutation relation, the commutator of Sx and Sy. It should give me I h bar Sz. So let's work it out. So what we have is Sx Sy minus Sy Sx, which is equal to h bar over 2 times 0, 1, 1, 0, h bar over 2, 0 minus I, 0, minus h bar over 2, 0 minus I, 0, h bar over 2, and you get 0, 1, 1, 0. Okay, so now if I work this out, I can factor out an h barred square over 4 out of everything, and then I now multiply the matrices. So if I do row column multiplication, I would get I. So I get I, and then I would get 0, and then I would get 0, and then I would get minus I. And then if I work out this second line, I would get minus, so I would get minus I, and then I would get 0, and then I would get 0, and then I would get I. Okay, so I can bring the minus sign in. So I have h bar squared over 4, and then I have I plus I, 0, 0, minus I inside my matrix. So now I have h bar squared over 4, the matrix 2I, 0, 0, 2, minus 2I. And if I factor out the 2I, then I get 2I times h bar squared over 4 times the matrix 1, 0, 0, minus 1. And so now I have, let's see, I h bar squared over 2, 1, 0, 0, minus 1. And if I separate it, I have I h bar times h bar over 2, the matrix 1, 0, 0, minus 1, which just happens to be I h bar Sz. So this choice of 2 by 2 matrices for the spin operators worked for this combination. You could work out the other cases now of things like Sy, Sz commutator should be equal to I h bar Sx, Sz, Sx should be the same thing as I h bar Sy. So it's going to be a fun exercise in matrix multiplication if you work this out. Okay, so those are the operators. Now if I look at our wave functions again, what we have, if you pick something like the electron, so it's 2 components, so it's a 2-component fermion. And so it has a component spin up, a component spin down. So then our wave function is really now a wave function spin up, so I'll call it psi plus, as a function of x, y, and z. And then as another component spin down, I'll call that psi minus components x, y, and z. I could actually write this in terms of unit matrices. So I would have psi plus times the vector 1, 0 plus psi minus times the vector 0, 1. So I could break it up into two parts. So a special name was given to these type of wave functions that are vector functions, and these are called spinors. So a spinor is just a special name for a vector wave function. It turns out that there is actually a whole field of mathematics that is built up around spinors. So it's not just that we use it in quantum mechanics. Mathematicians also spend a lot of time trying to find out the properties of spinors, which has actually helped out quantum mechanics quite a bit. So even though in physics the first times we see spinors are in quantum mechanics, but it also has other applications as well. Basically, it's the field of a vector of functions, and so now if we want to say operate on this spinor, then we could consider something like the momentum operator, the linear momentum operator. So say there's no angular momentum, orbital angular momentum, and so we just have the momentum operator operating on our wave function. What we would do is we'd have to write out the operator in a matrix. So the momentum becomes minus I h bar, the del operator. So because we have to take into account components in x, y, and z. Now it's a diagonal matrix because there aren't any cross terms. The momentum is just going to operate on each component of the spinor. Like so. So in the end, what you get is something that would look like a vector of minus I h bar del psi plus minus I h bar del psi minus. And that would be how you would approach solving this problem. You basically have now a vector of equations. So you could break it up. The easy thing probably to break it up and say, let's solve the x component, or I'm sorry, let's solve the spin up component. Let's solve the spin down component. Or you can leave it as matrices and work with them in that way. So if I look at, say, the z component, so let's do a transformation of the z component of spin. What happens when it operates on, now I'm going to write it as a state, not a wave function, but it's going to operate on this state psi. So that's the same thing as saying h bar over 2, 1, 0, 0, minus 1, operating on state psi plus, state psi minus, this vector of states. And if I work it out, I get h bar over 2. And then I would get, first I would get the psi plus, and then I would get a, oh, sorry. Let me fix that. I would get this vector of psi plus and minus psi minus. So the interesting thing is now I've transformed our vector of states where the rotation of the spin in the z component is going to not change. So the first one is not changed, but the second one now has a minus sign. So I've switched the sign. The sign gets negative. So spin up doesn't change. Spin down now carries a minus sign with it. So you can actually take that minus sign out and say that the operator on the state is going to give us eigenvalues of plus or minus h bar over 2, the state back again, like this. Or I could write it more succinctly by saying ms h bar. So now it looks like the z projection of the angular momentum, where now these quantum numbers ms is either +1 or -1. The eigenvalue of spin up is +1. The eigenvalue of spin down is -1. I'm sorry, 1/2. So spin up has a value of 1/2, positive 1/2. Spin down is a value of -1/2 for the quantum number. So it acts a lot like the projection of angular momentum in the z direction, but it's really now the spin. So that's why the little s subscript. So ms is the spin projection in the z direction, and it's either going to be spin up or it's going to be spin down. We could work it out, but since we already spent all the time working on orbital angular momentum, what we would find is that it's not the total spin, but the total spin squared is the thing that would actually commute with sz. So s squared commutes with sz. So that's a good combination of quantum numbers. Where s squared is sx squared plus sy squared plus sz squared. So we want the square of the total spin as a good operator, and not the total spin s. So anyway, so if we operate on with z squared on our spinners, I'll say plus or minus, then what we get is the eigenvalue of s plus 1 times the function back again, the spinners back again, just like we did for total angular momentum. So in this case, if we were to work it out, what we would get for s squared is h bar squared 1/2 times 1/2 plus 1. That's the spin up combination. 0, 0 minus 1/2. Oh no, not minus. So just 1/2, 1/2 plus 1. Sorry, there is no sign to the s squared. So s squared, I would get h bar squared 3/2, 3/4, 0, 0, 3/4, or 3/4 times h bar squared 1, 0, 0, 1, which is basically the identity. So anyway, so basically the takeaway is that when you operate with total angular momentum, total spin squared, you operate with s squared, what you get for an eigenvalue is s times s plus 1, just like we got for the total angular momentum case.